Hello, hello. All right. Good evening, everyone. Celso Batalha, Sotan, and I think some of you start observing the moon on Sunday, and the reason is we have some observing component in our course. For those of you who attended the observatory or and one of the lectures for extra credit, so you were safe. It's just a matter of sending us a report or send me a report through Turnitin, and the job is done. But otherwise, you must do a moon observation. So let me illustrate what exactly that is. If you go outside and if you look towards your western sky, you gotta be facing south, by the way. But if you face south and a little bit to the right hand side, which means you're facing your western sky, you might be able to see the moon in there. The moon should be at this time is about 8 o'clock. Should be um, 10, 15 degrees. So it's kind of a low because it's late, 8 o'clock. But you still can do your observation starting tonight if you haven't done yet. So basically, if you follow the instructions that I put in the video, you should have a paper sheet. Um, and the best way to do, let's see if I can go to, let me stop sharing my window now. And let me open a whiteboard. Okay, so let's say you saw my Starry Night, and what you do, of course, using rulers, and which I don't have here, you have a line that indicates your horizon. And if you're facing south, somewhere you have your south sky somewhere here, and your the moon, as we saw in Starry Night, was like this, right? Um, your western sky is somewhere in that direction, basically. That's your western sky, right? And then what you do, if you make a fist with your closed hand, you make a fist, and you place your fist at arm's length, that fist, so your arm must be straight. That fist projects about 10 degrees in the celestial sphere. So if you look towards your horizon, and the horizon is defined, is not the top of the trees. Horizon is, imagine there is a plane like a flat cardboard that pass through your eyes and then go and extend it out to infinity. So that line, this hypothetical cardboard, defines in your horizon, in your infinity. That's your horizon. Okay. In other words, if you're on top of a cliff and then you look out to the Pacific Ocean, all the way beyond the farthest you can see, where the line connecting sky and water meet, that's your horizon. And and that is also coinciding with this hypothetical cardboard that passed through your eyes. So if you have trees in front of you, if you have a building in front of you, your horizon is that line that hits the trees or the buildings, uh, parallel to the floor, passing through your eyes and extended out to the infinite. So this line here indicates my horizon, and its tick marks might indicate a fist. in that horizon. So it's about 10 degrees, right? So that would be 10 degrees. And I don't have my Wacom here with me. That's 20 degrees. And it's hard for me to write. This is 30 degrees. Oh, Harry, how are you? 40 degrees in there, so on, so on, so on. So you make these marks just to indicate how many degrees from due south objects in the sky are. And then you can do the same going up. So how many degrees is your object visible in the sky? So this you should go outside with a paper sheet like this, a red, nicely done, with a nice line here, horizontal, indicating your horizon, and this vertical line that might help you to scale the height, the altitude. It's fist indicating about 10 degrees. Okay. So if you place the moon right here, it means the moon would be 10, 20, 30, 40, 50, 60, 70, 80, 90, which is a lot. 90 degrees from some relative position, right? Which in my case I set due south. And the moon, if it's here, is about 10, 20, almost 30 degrees above your horizon. Okay. So let's say we observe this at 8:10. So you come here in your sheet and you mark 8:10 p.m. And the day is November 16, so that you know what you're doing. Okay. And then the point is, in 1 hour from now at 9:16, where is the moon located based on this outline? So you have to go back to the same spot, stand exactly in the same spot you were standing before, and then you observe the moon and see where it is. It's going to be here. What do you think it's going to be here? Or it's going to be there? Where do you think the moon is going to be? Okay. And then let's say the moon is here. You mark 9 and 10 because you observed 1 hour later, 9:10 p.m. of the day, November 16. And then you mark there. So that is your second observation. Here's the first one, second one. And then the third observation is going to be done tomorrow, also at 8:10, but next day, so 1 hour later. So you have to go back to the same spot, standing there, and then you find your moon, and then you do your little observation, okay? And then you see where the moon is. It's going to be here, it's going to be there, where is it going to be? And then you repeat the same exercise 1 week from today at the same time, 8:10. And then where the moon's going to be? And then you have to answer those 10 questions that I put in the sheet. So if you didn't go to the observatory, and if you cannot go to the observatory not this coming Friday, but the first Friday of December, that means you are doing observation. You have to, because observation is about 10% of your course grade. So make sure you do it. Either you go to the observatory and participate in our talks, which is simpler that way, or you do your observing assignment. Harry, this is the explanation I posted on the moon observation that is required to some of you in case you or the student didn't go to the observatory. My understanding is you already went to the observatory, right? And you need to submit a report or something based on what you saw there. And this is done. Let me show you what it is. Where is... right here. So if you go to our, oh, by the way, you can't see it right now. Let me open Starry Night. Okay, can you see my window now? Everything? Okay, very good. So basically that's it. So the moon is right there, you know, and then here's your horizon. You should have to write to establish this horizon, and then how many degrees is your moon from your horizon? For in this case, I mean I can mark, right? It's about 13 degrees is a fist, almost a fist and a half, basically. And then you have to find how many degrees the moon would be from your southern due south horizon. And but the explanation, the full explanation, is given in our Moodle course. Let me show you. And midterm 1 October. There you go, visiting the observatory. So that's what you gotta do. If you went to the observatory, I think that's your case. You should go to this turn in, and then you submit a paper, right? And then you have a submission in there. So far I have some people that submitted and I already correct, but not a lot, as you can see. Not a lot of you have done. Oh, you already completed. Yeah, you already done. Right, you already done. So I will start correcting this. I think it's easier to go to the observatory and participate there. That's the main point of this assignment, is to have you guys at least have a single experience of going to the observatory and observe some sky objects. If not, then then you have to do the moon observation, and the explanation about it is given right here. On November 9, you have moon observation required if you did not go to the observatory, and then you have a moon observation grade that I will post it, right? And then I already gave some explanation here, so just follow that and it should be fine. But you already went there, you are done with that part, so I'm not worried about you. All right? Good enough? Okay. All right, so the week today we are talking about evolution of high massive star on November 16, but in fact, um, stellar evolution is one of the key subjects of our course. And stars are not pretty much born out of nowhere, or they come out of a sudden and they stay there forever. In fact, the stars, they come and go. But this come and go, although it's not as short-lived like a firefly or a fruit fly, they take the most massive ones might take a few million years of life, as opposed to our sun that might take 10 billion years through its life cycle, or a low mass star, one that is less massive than the sun, might take hundreds of billions of years to complete its life cycle, which means the universe is not old enough to have so far observed the demise of one of these stars, because the universe is only 13 billion years of age. Um, the important aspect of stars is not only they are not eternal, but they also produce atoms. So stars, when they come and they formed out of the action of gravitational forces acting on the interstellar medium, so stars slowly and surely, that's what we learn in this course, they are formed, and then as the core, the stellar core, gets hot and dense enough, fusion reactions take place, and then hydrogen is converted into helium atoms. And then further down the line, when this helium is completely exhausted, then carbon and oxygen start to be produced. And depending on the mass of the star, there is this divide line of 8 solar masses. So stars that are less massive than 8 solar masses, they have a sequence of stellar evolution that is different from stars. There are more than 8 solar masses. So if the star is more than 8 solar masses, they are called high mass stars. They will evolve in such a way that the pressure on the core will be such that the star goes quickly through the different stages of fusion reactions in the core, producing not only carbon, oxygen, but neon, silicon, and ending up with an iron core, and to which point the star, the core implodes and the star explodes. And this phenomenon is called supernova. Um, so let me review the low mass star. Oh, I thought I had it. I thought I had it put in front of me. Now I can't find it. Let's see. Low mass star fused to carbon, high mass star fused further to iron. Yes, correct. Iron sucks up energy and bam, supernova leaving behind a neutron star or black hole, depending on the mass. Correct. I think you got all your homework already done, huh? Yeah, good for you. Good for you. No, I can't find my PowerPoint. Where is it? Take the Starry Night out. Take this out. Yep, I don't know what it is. Let's see. Yeah, no, it's not here. So should I do it again? Yeah, I think I'm gonna get it again. Sorry, I'm bubbling. Take this class notes. There you go. So in low mass star, I think you got the point, but I'm pretty much talking to students who are taking the chance of coming to this chat room and reviewing later on, just to know and to situate themselves. So in a nutshell, what's the main point of evolution in low mass stars? So imagine a star like the sun. Star like the sun is called a low mass star, and any star that is less than 8 solar masses is considered to be a low mass star. So in a low mass star, so a star that starts out with a overall material that is less than 8 solar masses, which means, so if you take the content of the sun, our star, the sun, the mass content of it, so the amount of hydrogen, oxygen, helium, and then you take that amount and you time 8. So imagine you can put together 8 stars identical like the sun in one single star. So that star has an 8 solar mass star, so it has a mass content that is equivalent to 8 times the mass of our sun. So stars that are less massive than this hypothetical star, they are considered low massive stars. And the evolutionary sequence of those stars is given here. So eventually, gravity is able to connect and to collect, in fact, material to allow for contraction to take place, and eventually a star is formed in the very core. And when that star is formed, um, to the point that in the very central core of the star, fusion reactions will start taking place. Because in a pre-main sequence phase, when the star is still contracting towards the point where fusion reactions will be initiated in the core, and then we call that phase a phase of a main sequence star like our sun is going through. So those phases, since the star is formed to the point that fusion reactions take place, we call that phase a pre-main sequence phase. So the star is still unstable, is still contracting, and then eventually this contraction will heat up the core, the 20% or so of the stellar radius right centered around the core, about 20%, that's the core. The pressure in there and the density and the temperature is such that fusion reactions will take place. So hydrogen atoms will be fused, and as a result of these fusion reactions, helium atoms will be formed. Plus, energy is released, plus a float of particles we call neutrinos. So the fusion reactions pretty much creates energy that is good enough to keep the star shining for a long time. If the sun were not a star, if the sun were a big chunk of charcoal, or if the sun was just uh, brightening and creating all this radiation as a result of a burning process, like a chemical process, the sun would be dead long time ago. So the sun still goes on for more than 4.5 billion years because this fusion reaction that goes on in the core is producing and providing energy that keeps the sun somewhat stable and will keep the sun stable for another 3 or 4 billion years in the future. And then eventually, the hydrogen in the core will be completely depleted. So I'm kind of advancing, but um, here is what a star is before its fusion reaction start, like our sun. So per mass, the universe has about 75% of hydrogen and 25% of helium. That's what you're seeing here. So most of the star in the beginning is hydrogen, 75%, and the remaining 25% is helium. And in the horizontal axis here, what we are seeing is the distance to the center. So surface is 1, right? And the center is 0. So the core is right there, it's about 20%. Once the sun or once the star initiate its fusion reactions, its core fusion reaction, then slowly the amount of hydrogen in the core is depleted because that hydrogen is fused, 4 atoms of hydrogen is fused into 1 atom of helium. Now the sun today, if you look at it here, the very central core, according to estimations made, is about 60% of helium, and only the remaining 35 or so percent is hydrogen in there. So eventually, in 5 billion years, the sun is going to be 100% in the very central part, helium. And then the amount of helium will eventually outcome and overcome and overshoot that of hydrogen. So when the sun gets to the point that most of the core is populated by helium atoms, then the fuel of that fusion reactions, which is hydrogen, is gone. It's all exhausted. Like you start the day with your wallet full of $20 bill, and then you have good friends when you have that much money. And then you spend that much money. End of the day, you don't have that anymore. So some changes are supposed to occur. In the case of the sun, since that production of energy is exhausted, is gone, because the fuel is gone, hydrogen is gone, now you have helium, changes will occur. And what occur in the case of the sun is the following. The core itself, the central part of the sun itself, will contract because now the weight of the entire star will be act upon that core, squeezing it, forcing it to contract even further. And one of the uh, laws of thermodynamics of gas is that when you contract gas, gas heats up because you are forcing the atoms to collide among themselves. And collision in physics is translated into temperature rise. So it gets hot. But as this core contracts and heats up, there is a shell. Let's see if I can expand this. There is a shell, hydrogen burning shell, that surrounds the core that is now contracting. And this hydrogen burning shell initiate, I mean, when we call burning, it means fusion reactions. So these fusion reactions produce energy that outcome the energy that was being produced before. So basically, out of the core of these stars, more energy floats away than it used to float before. And what is the main result of this? Well, um, if, if, if you can think of a shell anywhere in the middle part of the star, like here, so the outward force that is produced by this float of energy that comes out of the core forces this outer shell into an expansion, overcoming the weight of the star at that level. Because the star is in balance, the size of the star is always the same. If there is a perfect balance between the outward pressure that is caused by energy stored in the star itself against the weight of the star. So if these two forces, the outward pressure and the weight, are the same, then the star is balanced. But now we are talking about a surplus of energy that comes out of the core, and that it will force the outer shell into an expansion. So basically, in a low mass star, when the fusion reactions in the core ends, the core contracts, the outer layer expands, and once gas expands, and this is also laws of thermodynamics, once gas expands, gas cools down because you have less collisions happening. So the outer shell becomes cooler, and less temperature for stars, as far as star is concerned, it means the star becomes redder. So the star is called a red giant. So this is what we were talking about. And this star is called a red giant. So a red giant has a core. Now this is the main sequence. Oops, what happened? This is the main sequence that has a hydrogen burning core and an envelope, right? So when you go to the red giant, the core is um, is not is not burning anymore. So you don't have that fusion reactions happening exactly in the core. But there is a hydrogen burning shell around the core itself. And that is what is responsible for this expansion of the star and the cooling down of its outer shell, which kind of seems to be two opposite situations, right? So the core contracts and heats up, the outer shell expands and cools down. All right. Uh, Now, in the case of a low mass star, let me see if Hardy has anything to say. Let me see if I can find my way to the chat room. Okay. Oh, you put something there. Okay, let me see. Are you enjoying? You are having problems with the internet, so you are coming in and out. Okay, basically in the core, hydrogen fuse resulting helium core with hydrogen burning shell. Yes, core shrinks and heats up and helium start to fuse. Yeah, so helium will start fusing when the core reaches about 100 million Kelvin. Usually the sun, the core is about 20 million Kelvin, and that is the temperature in which fusion reactions now take place, and that is the temperature the core will have when it's completely filled with helium. So at that temperature, helium will not fuse itself into carbon and oxygen. So once the core starts contracting, now the temperature rises up from 20 million to 100 million. And when that level is reached, then the pressure, in addition to this high temperature, is just good enough to ignite helium fusion reactions. The problem with the low mass star is, I think you, okay, let me see if I keep reading here. Now, carbon core, yes, once helium starts fusing to carbon core with helium burning shell, yes. Yeah. The star is not shrinking. What's shrinking is the core. The core shrinks, but not the star. So 20% of the solar radius. So the sun is 100 times, just to give an idea, the sun is 100 times, as far as diameter is concerned, 100 times bigger than Earth, right? So 20% of the sun is something that has a diameter that is 20 times the diameter of our planet Earth, okay? Because the sun is 100 times bigger than Earth. So 20% of the sun is core. So 20% we are talking about some volume, some big chunk of thing that is about 20 times bigger than our planet as far as diameter is concerned. But here's the thing: when the core start contracting to the point of initiate further fusion reactions of helium and further down the line helium into carbon and oxygen, the final result, the final product is what we call a white dwarf. A white dwarf is a star that is a corpse of a low mass star like our sun. And a white dwarf has the dimensions of our planet Earth. So what I'm trying to say is that when the core itself stopped all fusion reactions of hydrogen, the core was about 20% the stellar radius. And that was reduced all the way to, 20 times to the point of a white dwarf. So we have further contraction and reducing. So the core shrinks, but the star itself expands. And to the point that when you are reaching the point of a white dwarf, several episodes of flash leads to the release of gas from the star, producing what we call planetary nebula. So planetary nebula is a stage in the evolution of low mass star when this entire outer shell right here is released. It's pretty much thrown back to the interstellar medium, not only with the same gas content that it had when the star was formed, but that in addition to freshly formed carbon and oxygen the star itself produced. Okay, yeah, in that phase is the red giant, correct. Very good. Now, the fusion reactions in the case of a low mass star, the helium fusion reactions, is an interesting aspect because it doesn't start right away. In fact, the core it becomes degenerated in the sense that all the atoms are packing up in such a way that in response to this building up pressure. So the helium starts fusing into carbon in a process called triple alpha process. In fact, that was envisioned by Fred Hoyle. He's a physicist, and and but it doesn't happen only on the shell, but it happened. These fusion reactions is ignited all over the core. And the reason is you have the same conditions of pressure and temperature throughout the core. The core is packed in such a way that no more contraction can happen. And that moment in which the core light up is called flash because it's done in a short amount of time. And then these fusion reactions again start in the core, but at this time not hydrogen, is helium. So the helium goes in these fusion reactions in a very short amount of time, and according to calculation, is done in a few seconds. We have the whole core lighting up. So some sphere that is comparable to that of the entire planet Earth suddenly ignited in what we call flash. Um, and from there, the star becomes again somewhat stable because the core now is producing energy in some stable way. The core is not shrinking anymore, it's pretty much stable and has fusion reactions going on, except these fusion reactions don't take as long as it did for the hydrogen. So it ends quickly. And for a low mass star, it ends to the point the star itself don't have enough conditions to exert pressure on the core to ignite carbon fusion reactions. So that's it. So now we have a core which is a white dwarf that is pretty hot, about 100,000 kelvins or so, and that star becomes what's called a white dwarf, and the outer shell is expelled away in several episodes lasting or separated by hundreds of thousands of years. And this gas eventually is completely um, returned to the interstellar medium, and we have one of the most beautiful pictures in the universe that I think that's my take is that of a planetary nebula. Let me show you. So if you Google planetary nebula, they are really gorgeous. Look at this. Aren't they gorgeous? They're quite something. So of course all these colors, some of them are fake colors, but astronomers do that to highlight different parts of the gas and different processes going on. But as you can see, these episodes of expanding material, it happens in response also not only to the energetics that goes on in the core, but also to whatever remaining magnetic fields the star has in itself. Because all these different morphologies you can see here, all these different shapes, are driven by magnetic fields and by external and the way these flash or these explosions occur in the star. So this looks like an hourly glass, right? Another one here. Look at this. Aren't they gorgeous? I think they are gorgeous. Look at that one. Quite something. I think this is funny. I don't understand that. Planetary nebula. This is what they are. So look at this. How many episodes of explosion has gone through? So I don't know. This is spacetelescope.org. And that looks like an egg. Looks like an egg yolk and white. Something in there. So they are cool. They are really cool. What is this? Look at this one. Isn't that cool? I think they are. So low mass star, it goes that way. High mass star, which is this week, is a little bit more complicated. In a way, it's simpler because it doesn't go to the helium flash. So the fusion reactions go one after the other. And then the final product, as Harry, you mentioned in the very beginning, is a corpse that is not a white dwarf, but is a neutron star or a black hole. Neutron stars are stars that are made of neutron atoms, and neutrons are particles that are part of the atomic nucleus. So neutron stars are the most dense objects we know in the universe, not including black holes, because black holes density doesn't make sense to talk about it. So, but neutron star has a density that is the density of atomic nucleus, and the size of neutron star, few tenths of a mile. They are very short. They are very compact, and they rotate fast. They have strong magnetic fields around them, and and uh, and they were first observed as pulsars um, because they could be observed rotating very fast in few microseconds and releasing vast amounts of radiation in the radio band. And now also you can perceive that in other optical bands. So where are we now? Yeah, no kidding. I think it is. So white dwarf is a non-burning carbon core, yes, that is left behind after red giant throws off its outer layer. Yes. And the form, yes, 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 yes. So you got it. That's what it is. And they are cool. I mean, they are really cool. Um, so see this little thing right here in the center? This little thing right here in the center is a white dwarf. This is a white dwarf. So if you look at this planetary nebula, see this one over here? That's a white dwarf right there. And it's a white dwarf right there, surrounded still by some mass. So this I can't see it, but it should have a white dwarf there. So all this planetary nebula, you got a bunch of gas coming out of it. That's a white dwarf right there. It's a bunch of gas that is surrounding a white dwarf. It's right there, white dwarf. And that's cool. Look at this. Isn't that cool? Looks like a, what's the name of that? Jellyfish? It is a jellyfish. Jellyfish in the space. I think this is crazy. I think there's a lot of production here. Come on, looks like a, you know that thing you put around the cake to avoid flies on it? It's a white dwarf right there, little thing. All right, it's the one right there. It's a gnarly glass. This is pretty much controlled by magnetic fields. So magnetic fields are those who create this type of thing. Okie dokie. All right, so let me see if I have anything going on in the class. Um, so we are in November 16. So next week we are moving out to galaxies. November 23rd is pretty much galaxies, um, and we have a spring break. Oh, not spring break. What I'm talking about, Thanksgiving. Thanksgiving. So basically, we don't have much going on, but then we have an exam coming up so far, don't we? I thought we have an exam. We did exam number 2 next week, right? November 2, 16. Yeah, 23rd. Yeah. So the exam next week is going to be, because I give exam in 2 episodes, Thursday and Friday, right? But next week, just confirm this. Next week is Thanksgiving. Let me see, 16. Yeah. So next week's Thanksgiving. So the exam is gonna be on Monday, the 23rd, and then I will repeat on the 25th. Thanks for reminding me that. So I have to email the class and let them know about it. So yeah. So the exam number 3, the last one, is gonna be focusing on stars, sun and stars in general, and I will repeat or give a second attempt on the 25th. Um, yes. That's it. All right. In fact, I will email the class now. All right. Nice. Good night. Good night to you, and hope you see you on December. Can make it to the black holes. It's gonna be the topic of the talk: black holes. All right, Harry. Good night. Oh, okay. All right. Yeah, it's getting really cold. It's getting extremely cold. But we have a very dry season. Last year, at this time, we didn't have observatory at all. It was always wet or cloudy. But yeah, the climate change is really helping astronomers. All right, good night.